sharing. Today's topic is heat generation in sphere. Imagine a tiny solid sphere that continuously generates heat within itself, much like the core of the earth or a nuclear fuel pellet. But how does this heat distribute inside the sphere? Where is the temperature highest and how can we visualize it? In this explanation, we will uncover the secrets of heat conduction in a sphere step by step using mathematical models and Python simulations. We'll first plot a simple temperature graph and then reveal a beautiful contour graph that paints the complete thermal picture. So before we dive into the coding, let's break down the physics behind it. Heat conduction in solid sphere with uniform internal heat generation is governed by the well-known equation as you can see in the screen. So the equation describes how heat moves inside a sphere. But what do these terms mean? Let us understand that. T is for temperature at a given point. R is radial position measured from the center of a sphere. Q is heat generation rate per unit volume, W by m cube. K is thermal conductivity, which tells us how easily heat moves through the material. Solving this equation gives us a temperature distribution inside the sphere. As you can see, the equation of the temperature distribution. Ts is the surface temperature and R is the sphere's radius. This equation tells us the temperature is highest at the center, R equals to 0, and decreases towards the outer surface, R equals to R. Let's do some coding then. So this Python code simulates the steady state temperature distribution inside a solid sphere with uniform internal heat generation. The goal is to understand how temperature varies from center to outer surface. So first we are importing some libraries for plotting and mathematical operations. Then we are defining the problem parameters here, where r equals to 0.1 meter, sphere has the radius of 10 centimeter, k equals to 200, material has a high thermal conductivity, example like metals like copper. Then we have q equals to 10 raised to 6 w divided by mq. A high rate of heat generation common in processes like nuclear reactions. Then we have Ts 300 K. The sphere's surface is maintained at 300 K due to the cooling. And then we are defining the radial positions here. So it will create an array of 100 points evenly spaced between r equals to 0, which is center, and r equals to r, which is the surface. This helps in smooth visualization of a temperature profile. Then we have temperature distribution equation, as we have already seen. So Ts is the surface temperature 300 K. R square minus R square describes how temperature changes radially. Then we have Q by 6K scales the heat generation effect. So here it is mentioned at R equals to 0 in the center, the equation is this, and for at R equals to R surface, the equation will simplify to this. Okay. This confirms that the maximum temperature is at the center and the temperature drops towards the surface. Now we can plot the temperature. Here we are creating a figure and plotting temperature versus radial positions. And now let's run the code and see how our figure is. So while it is running, let's understand. So okay, it is there. So here we have a radius versus temperature graph, and let's understand the graph. The x-axis represents the radial position inside the sphere from r equals to 0 to r equals to r. The y-axis represents the temperature at each radial position. The curve starts at maximum temperature at r equals to 0 and gradually decreases towards the surface. The surface temperature is fixed at Ts equals to 300 K. Why does the temperature drop from center to surface? Because heat is generated uniformly inside the sphere. Heat flows readily outward, leading to a temperature gradient. Okay. So now we are calculating contour plot of temperature distribution in a sphere. This Python script visualizes the temperature distribution in a solid sphere using contour plot. It represents 2D cross section of sphere, helping us to see how temperature varies inside the sphere due to uniform internal heat generation. So first, understanding the problem, heat generation in sphere. We are dealing with a solid sphere where heat is being generated uniformly within its volume. This type of problem appears in nuclear reactor, biological systems, battery, thermal management. The steady state heat conduction equation in spherical coordinates with internal heat generation. So here is the equation given for that, and solving this equation gives the temperature distribution. It is also given there where Tr is a temperature at a given radius, R is the total radius of sphere, Ts is the surface temperature of sphere, U is heat generation rate per unit volume, K is thermal conductivity of material, and the temperature is maximum at the center and decreases towards the surface. So this is the code for it. So we have imported some libraries, and then we are creating a 2D grid for visualization here. So here this NP line space creates 200 different points from minus r to r along with x and y axis, and this mesh grid creates 2D arrays x and y representing the coordinate grid covering the circular region here. Okay, and this grid allows us to compute temperature values at various points inside a sphere. Now to compute radial distance from center, we are using this equation. So what is happening here, since our temperature distribution depends on the radial distance r, we calculate r, and this formula finds the distance from center 0 0 for each point on the grid. The result is a 2D array of a radial distance from the sphere center. Okay, and then we compute the temperature distribution, and for that we are using this full like function, which will create an array in the same shape as R but filled with Ts, the surface temperature, which ensures that the points outside the sphere stays at Ts. And then we have mask, creates a boolean mask true for inside the sphere and false points for outside the sphere. The only points inside the sphere should follow the temperature equation, and these will apply temperature equation only inside the sphere. Points outside the sphere remain at Ts. This ensures our contour plot evenly only displays temperature within the physical sphere. And now we are creating a plot, and we are drawing it using Python code here, and let's interpret what is happening here. So the color gradient represents the temperature distribution. The brightest hottest region is at the center of the sphere, and it gradually decreases as we move outwards. The black boundary represents the physical sphere's surface. The temperature is lowest at Ts, Why the center is hotter? The heat is generated inside the sphere, and heat must flow outwards through the conduction process. The center has highest temperature because heat cannot escape easily. So, what are the key takeaways from this tutorial? Contour plot provides clear visualization of temperature distribution inside a sphere. The highest temperature is at the center and the lowest at the surface. The simulation is useful for engineering applications like nuclear reactors, battery, and biological studies. Would you like to add, we can have next session on add heat flux calculations or moderate transient heat conduction, apply different boundary conditions? Then let us know in the comments and we'll add it in our next lecture series. Thank you.